All right, so the first way that you're going to look and see what the limit of something is just graphically. I will say that I didn't catch it when I looked at the answer key, but I'm going to show you this number 6 for a reason, because right now we've really only talked about overall limits, not left and right-handed limits. And so the first one, as x approaches 1. So the first thing you're going to do is say, where is my x going? All right, my x is moving towards 1 from the left and the right. So what I typically do is I find 1 on my x-axis, and I'll just draw a line down that guy right there, and then you can quickly see what that graph is approaching, all right? It does not matter that there is a hole at x equals 1. It matters that if I were to travel down one side of the graph or up the other side of the graph, they're both going towards that same number. Specifically, what number are they both going towards? We know that x is going towards 1. They told you that. I'm asking what y is doing, right? So limit is always asking about the output, okay? So you're not going to tell me 1 because I told you 1, right? So you're going to tell me -5, all right? So the limit here, as x approaches 1, y is approaching -5. So if I am asking for overall limit, so we are just going to pretend that this little minus sign is not there. See, it's not there. All right, it's gone. So they want the limit as x approaches 0. So once again, I am going to go and I am going to draw my vertical line at x equals 0. For an overall limit, they have to be approaching the same thing. So if I were to travel down this graph from the left-hand side, I would see y is going towards +4. But if I were to travel from the right-hand side and go up this graph, I would see that y is approaching +6. I have a problem. An overall limit does not exist here because they're approaching two different things. I have a limit from the right, I have a limit from the left, but if I'm talking about overall limit, I don't have one because they don't meet. They have to meet for there to be an overall limit, okay? Or this particular graph could have an overall limit somewhere else. As x is approaching -6, there's a limit, right? Because they're approaching the same thing from the left and the right. But specifically here, there is no overall limit. And so for this one, you would write something like does not exist. Or for my math people who, absolutely hate writing, there you go. All right, algebraically, the very first thing you're going to say is, can I just plug this guy in, right? If I can plug him in, I'm going to do basic order of operations here, okay? And so I look at this first one, number 7, 0 doesn't cause a problem here. So to find the limit, I can just say, well, 2 times 0 minus 5. And I am done. Right? But if I look at the next one, number 12, plugging in a -3 definitely causes a problem. If I just plug it in, then I have a 0 in the denominator. This is then where you're going to say, can I factor it? And so we're going to go to our factoring method, and we're going to say, well, factors of 12 that add up to 7. Don't forget, by the way, this is the most common error on these. If there's a little tiny negative in front, I would recommend highlighting him so that you remember there's a negative in front of your answer. So factors of 12 that add up to 7 look like this. In the denominator, I have x plus 3. Don't forget you're finding overall limit here. Still have a problem, but now I see I can cancel my problem out. If I cancel my problem out, now I can just plug it in. Again, number 1 problem's that little guy. So we have a negative in parentheses, -3 plus 4. -3 plus 4 is 1. And then apply that negative in front of it. My answer is -1. So the third type that you're really going to run into is something that looks like this. Obviously, you're not going to factor him, but we can use conjugates, all right? I promise you, I'm not trying to trick you. If you see a square root, likely going to use a conjugate method, right? I'm just trying to get you to practice these methods. And so For this one, I clearly have a problem if I just plug in a 1. Now, I want you to try, I mean, you could have one where you could plug it in, but if I plug in a 1, I have square root of 4 minus 2, we have a problem in the denominator. So I am now going to use the method to multiply by the conjugates. All right, remember that if you multiply by conjugates, you get the square of the first minus the square of the second. For the other piece of it, whether it's the numerator or the denominator, if it is not the conjugate you're multiplying, don't FOIL it, because you're going to get rid of your problem and it's not going to require you to FOIL to do it. You're only FOILing or multiplying the conjugates themselves. So in that numerator, I'm actually going to leave that x minus 1 alone with the square root of x plus 3 plus 2. Leave all that alone. In the denominator, I am going to actually multiply them, but that's easy. It's the square of the first. When you square a square root, it just goes away. So I have x plus 3 minus the square of the second. 2 squared is 4. And so when I simplify that denominator, you can see that I'm going to be able to get rid of that x minus 1, right? And of course, we are still finding the limit as x approaches 1. So when I cancel out my problem, I can now just plug it in, right? And so I have 1 plus 3 in the root there, which is the square root of 4, or 2, plus 2. My answer here is 4. All right, so the first thing that we're going to do with slope of the tangent line is at a specific point, all right? Now remember, with sections 3 and 4, we did the long method, and I told you I'm not going to make you calculate them out the long way, all right? So you can use your shortcuts here. But anytime you see, in calculus, you see slope of the tangent line, you are going to first take the derivative, all right? So we're going to take the derivative using our shortcuts. And then we are going to plug in the x value that they gave us, or the point that we are trying to find the slope of the tangent line at that point, all right? So remember, derivatives, we have shortcuts. We multiply everything by this exponent, so bring that guy in front. Negative 2 times 2 is negative 4. And then for my new exponent, I subtract 1. So 2 minus 1, my new exponent is 1. Plus, the exponent on this is 1, so we multiply through. 4 times 1 is 4. My new exponent is 0, so my x goes away for that one. And then remember, the derivative of a constant is 0. So that guy just drops off completely, all right? So we're multiplying by the exponents, and then our new exponent just goes down by 1. And that is my derivative. So I already have my derivative. Now to find the slope, I'm not done. To find the slope of the tangent line, I'm going to take the point that they gave me, and I'm going to plug it in to my derivative. So I'm going to say negative 4 times 1 plus 4, 0. The slope of the tangent line there is 0. All right, so number 24, it says for each function, find the function for the slope of the tangent line at any point. So now I'm not giving you a specific point. You're not going to give me a specific number necessarily. I want a new function. So I actually want the function itself. And so when I look at this looks very familiar, but when I look at this, I am literally just looking for the derivative. So we are going to do that process. 2 times 4 is 8, x to the first power, minus 1 times negative 2 is negative 2, x to the 0. That 4 drops off because the derivative of any constant is just 0, and I'm done. So I'm just trying to get you used to the language, all right? The function for the slope of the tangent line at any point is just the derivative. It's just another way to say derivative, all right? For each problem, find the instantaneous rate of change of the function at the given value. What is your rate of change? What's another way of saying that in pre-calculus world? Rate of change. So for this one, you're literally doing exactly what you did on 19 through 22. You're finding the first derivative, you're plugging in the point that they gave you. And that is the instantaneous slope or slope of the tangent line. It's the same thing. So You will feel like you have done this a million times, but it's okay. We're going to multiply by our exponent 4, drop our exponent by 1. My coefficient of my x is just a 1. That's what it ends up being. Constants always drop off. That's my function to find the instantaneous rate of change. We're just going to plug that guy in. So 4 times 1 plus 1 equals 5. That is my instantaneous rate of change. Anytime you have ones that are a little weird, whether it's a radical or whether it's a variable in the denominator, before you take the derivative, you need to rewrite them, okay? So for this one, before I ever go to f prime of x, I'm going to rewrite this guy here. Instead of the 5th root of x, what do you think I'm going to write? X to the 1/5, okay? So rewrite it. And then the process is the same. Now I'm ready to take the derivative, right? So I'm going to do the same thing. Multiply that through. That's 2x to the 1 plus 1/5 times 1/4. What do I get when I multiply 1/5 times 1/4? Yeah. So 1/20. And then x to the 1/5 minus 1, which is like minus 5/5. So what is 1/5 minus 5? Negative 4/5. That is not pretty, so we are going to rewrite it. I don't mind if you leave it as a radical or as a fractional exponent, but I don't want a negative exponent, okay? So you can do it two ways. You can either do it like this, 1 over 20 x to the 4/5, or you could say 2x plus, that's a 20, 1 over 20 5th root of x to the 4th. I don't care. I think your answer key leaves it like this, so.